Welcome everyone, re-welcome everyone to the KNI 20th anniversary celebration. How many of you were able to come to the fireside chat between our president and George Whitesides? What a way to kick off the event, huh? That was the perfect beginning of our celebration. Today's format is going to be more like a Gordon-style conference, those of you who have been. So we're going to have some very exciting talks. KNI is a very interdisciplinary and multidisciplinary place, and we'll welcome all kinds of nanoscience, and today we'll hear talks of all facets of nanoscience. We're going to have a poster session where everyone will be able to vote for their top choice. They're mainly presented by our early career researchers, by our grad students and postdocs. We're going to have a surprise video that I don't think anyone here besides us has seen. And we're going to have a panel discussion. So every kind of a scientifically oriented and socially oriented activity will be available here for you today. And I hope that you can walk on the beautiful walkway in this beautiful weather that we arranged for you, and check out our banners where each image is different and it belongs to a particular research group here at Caltech. In fact, the PIs might be here, maybe even the grad students that took these images might be here. I wanted to share with you a little bit about what the KNI has been doing in the last couple of years. So about 10% of our faculty are members of the KNI right now. Our facility draws researchers from a variety of different disciplines, from biology and chemistry to all kinds of engineering and astronomy. Once the users are trained, they're able to have access to these instruments that we have available in the clean room. They have the ability to try out cutting-edge technologies and to pursue research that has not been maybe provided for them by the manufacturer. There's no recipe for the kind of research that happens at Caltech. Besides Caltech users, we have JPL users. We have we help startup companies get started. We have users from Samsung and Meta and Nokia and several others. And most recently, we started partnering with Amazon Web Services, with AWS, of course, being a huge partner and a user in our clean room. So the kinds of research that we do here ranges from prototyping new materials that can resist impact or store energy, to growing and characterizing quantum materials and two-dimensional van der Waals materials for topological quantum devices, nanophotonics, identifying rare proteins, and building nanodevices that can connect single photons to individual atoms, and one that can store and release photons on demand. So with a huge token of gratitude to the Kavli Foundation, who has been supporting us all the way, I would like to now introduce our discussion leader, who is a Caltech alum. So I'm particularly happy and honored to introduce my friend and colleague, Professor Dionne, who is the Senior Associate Vice Provost of Research Platforms and Shared Facilities, and an Associate Professor of Material Science and Engineering and of Radiology, my God, Jen, at Stanford. Jen received her Ph.D. in Applied Physics, which is our department here. She was in the group of Harry Atwater, who of course now is our division chair and one of the cognizant officers for the KNI facility. And Jen has way too many awards, but I'd like to point out some of the really important ones. So like the Alan Waterman Award in 2019, this is the highest honor that the NSF bestows upon young faculty members. The NIH Director's New Innovator Award in 2019, a More Inventorship Award, and many, many others. So I'm very happy to welcome you back to your PhD alma mater, and please take it away.
All right. Thank you, Julia. All right, it's such a pleasure to be here. Thank you so much, Julia, for that amazing introduction. Thanks to all of you for coming to the KNI 20th year anniversary event. Like Julia mentioned, I did my PhD here around the time that the Caltech was KNI was just getting off the ground, and I remember going into the basement of Steel when there were just a couple of tools like e-beam writers, focus ion beam, deposition tools, and the whole basement was pretty much gutted except for these few select rooms, and it definitely taught me so much about nanoscience and building a lab from the bottom up, and it's incredible to see what the KNI at Caltech has accomplished in the last 20 years. I was told for this introduction to discuss a tiny bit about me, give some context on the session, and then also introduce our speaker, and to do so in 5 minutes. So buckle up, because this will be a whirlwind tour. So a bit about me. You heard Julia say I'm a faculty member in material science and engineering, also in radiology at Stanford University. But I didn't always know I wanted to be a professor. I grew up in Rhode Island and was inspired by special agents Fox Mulder and Dana Scully on the X-Files. And I loved how you had an FBI agent and a physician working together as a team to solve problems, and that's something I try to emulate in my own work now, doing collaborative research across multiple disciplines. But inspired by them, I thought I wanted to be either a paranormal researcher or some sort of performer, and eventually make my way out to Hollywood. So on the performing side, I did a lot of figure skating, and I also loved doing magic tricks when I was growing up, so I thought I wanted to be a skating magician, and I thought I could bring that over to Hollywood. Didn't quite pan out, but in 2003, I did get called by a nearby casting agency, Caltech. And of course, many of you know Caltech is known for its pranks, so this is the Hollywood sign that was blacked out in the Hollywood Hills with Caltech over it. I was not here for that particular prank, but later on in my talk, you'll get to hear about another one that I was here to witness. And while I never did quite make it to Hollywood, I got lucky enough to meet quite a few stars and science stars along the way. I think Numbers was being filmed here when I was a graduate student. And then I remember getting up at 4 in the morning to get tickets to see Stephen Hawking for his talk when he was here. And then I got to meet the Mythbusters folks. So I have many warm memories of Caltech. And among several topics in my research lab, I'm really interested in sculpting light at the nanoscale, both to detect molecules and to direct their transformations. And I view myself essentially as a tool builder for the physical scientists, chemical scientists, and life scientists. And this is one such tool that I've had the chance to work on and really build from the bottom up at Stanford. It is an environmental transmission electron microscope, so it allows you to do atomic scale imaging in reactive gaseous environments. So we've been able to introduce different gases, also introduce light, introduce biases, and look at photoelectrocatalysts in the TEM and how molecules are interacting with the catalyst. And then what we do is we can link that to reactor scale performance. And if any of you have gone to the Exxons or the Dows of the world, you know reactors are generally the size of buildings. In our lab, we have more benchtop size reactors, but we try to understand the whole length scale and time scale of how these reactions are occurring in order to optimize them. And although I am by no means an expert in this session topic, next energy storage materials and architectures, I think there's a lot of that same underlying multi-scale physics and multi-scale chemistry where you need to understand everything from what's happening within the electrode, of a battery to what's happening, on length scales comparable to the size of batteries that, can be the size of a room sometimes. But to provide a bit of context on this particular session, I wanted to consider a little bit of the history of energy storage materials and where they've gotten us now. And yesterday at the fireside chat with George Whitesides, he was mentioning, I imagine all of you have a cell phone in your pocket, and we all do, and we might complain that the battery doesn't last as long as we like it to. But if you go all the way back to 1983, when Michael Douglas, on The Wolf of Wall Street, carried his brick phone, the Dynatac phone, we know that batteries have come quite a long way. So the first commercial cell phone was the Dynatac. It was about maybe 1 foot or 9 inches long, weighed 2.5 pounds. It could store 30 phone numbers, so it certainly was not quite a computer at the time. Cost $4,000 in 1983 dollars. That would be the equivalent of about $12,000 today. And a single charge single charge took about 10 hours. Now, since we're at Caltech, and I remember a lot of pop quizzes when I was a student here, I want to ask you a pop quiz. What was the battery lifetime of the Dynatac phone? So we knew, or we just saw it takes about 10 hours to charge up. Was the battery lifetime equivalent to what now is the 10K world record, which is about 25 minutes? Equivalent to the length of the first feature film, which was filmed at the Athenaeum, but in Australia, not the Athenaeum here, which is the story of Kelly Gang, 60 minutes, or equivalent to the record English Channel Swim, which takes about 6 hours and 55 minutes. So maybe show of hands, who thinks the battery time was the 10K world record time? Okay, just a couple people. What about the first feature film? Oh, a few more people. And the English Channel Swim? A handful of people. Okay, so turns out it was about 25 minutes long. So congrats to those of you who were brave enough to raise your hand first. Okay, and then finally, if the Dynatac battery had the capacity of the iPhone lithium-ion battery today, how much would it weigh? And the capacity is usually measured in milliamp hours. It's basically how much electrons or how much charge a battery can hold. So if we kind of scale the capacity of the original Dynatac phone battery up to what we could have today, do you think it would weigh as much as a LED flat screen TV, one of the big ones, which is about 75 pounds, as much as a newborn elephant, which is 200 pounds, or as much as the Caltech Fleming cannon, which was the prank that happened when I was a student here? That cannon got moved to MIT because apparently MIT students were upset that Caltech students had gone during their admissions day and handed out t-shirts that said MIT on the front and on the back said, because not everyone can get into Caltech. So MIT students came out here and started to move the cannon. I don't know how they did it because it weighs 900 pounds. And accordingly, or according to folklore, I don't know if this is true, Julia can comment, Caltech security just asked the students, hey, what's going on? And the students were like, oh, we were asked by the president to move it to the other side of campus. So it went into the U-Haul and got driven over to MIT. And then I don't know who was president at the time, maybe Jean-Loup, but apparently the presidents of MIT and Caltech had to get on a phone and eventually say, look, this is a war-era artifact and cannon. We need it back here at Caltech. So it is returned. I saw it this morning on my run. But anyway, alas, back to the question, now that you've had a chance to think about it. Yeah, if the Dynatac phone battery had the same capacity as today's iPhone, how much would it weigh? Who thinks 75 pounds? Okay, a couple people. Who thinks 200 pounds? A couple more people. And who thinks 900 pounds? Awesome, you guys are smart. You're Caltech folks. So yeah, it would weigh 900 pounds. And of course, we've seen tremendous advances, in commercial energy storage devices, not only from our phones and laptops, but of course to electrification of vehicles. And what I think is really interesting is we're seeing this transition not just from consumer products, but across all industries to electrification. So here are the greenhouse gas and CO2 emissions in 2021 from California. And you can see a good number of the emissions come from the transportation sector, so it's exciting to see what's happened in the electric vehicle sector. There are also a lot of emissions that come from industry, whether chemical manufacturing or making construction materials like steel and concrete, and then kind of building, heating and cooling. That is also a big emitting industry and one where energy storage is going to play a pretty important role. And at least in California, wind and solar, are quite abundant. And it really becomes a matter of not generating energy, but storing that energy. And today we'll get to hear about a lot of incredible advances that are happening in Dr. Shirley Meng's lab in designing new energy storage materials. So Dr. Shirley Meng is currently the professor of molecular engineering at the University of Chicago. She did her undergraduate degree in Singapore at Nanyang Technical University and did her Ph.D. at the MIT Singapore Alliance in material science. And then she started, I believe, as a professor in energy technologies at the University of San Diego before being recruited to the University of Chicago. And at the University of Chicago, as well as at UCSD, she runs the Laboratory for Energy Storage and Conversion. We have never had the chance to meet in person, but I've long admired her work. It's really inspiring how she takes this multi-scale, multi-pronged approach to understanding energy storage materials and improving them in devices. Among her numerous roles and responsibilities, she serves currently as the chief scientist of the Argonne Collaborative Center for Energy Storage Science, or ACCESS. She's also an ECS Battery Division awardee. She received that award last year. And then she also won the C3E Technology and Innovation Award in 2022, I believe, and the International Battery Association Research Award. She's a fellow of numerous societies, including the Materials Research Society, the AAAS, and the Electrochemical Society. And in addition to receiving funding from many of our federal agencies and private foundations, she also has partnered closely with industry, which is part of what I think is what makes her work so inspiring, that she's addressing real challenges and pain points that are in industry, so that way what she develops in the lab can be translated into the field. So you can see here some of the industrial partners that she's worked with, like LG Energy Solutions, Thermo Fisher, Shell, Nissan, GM, Applied Materials. And as sketched out here, you can see she takes an approach where she goes from the electronic level to the atomic level to the single particle level to the electrode level in these energy storage materials. So Shirley, thank you so much for coming here, and the floor is yours.
Thanks to the Kavli Nanoscience Institute in Caltech. Every time I come to Caltech, I believe the first time was the time I met Stephen Hawking on this campus. So it's a place of magic. You never know who you're going to meet next, and always a pleasure to come back. So thank you, Julia, for having me back. I took the job in University of Chicago about 2 years ago, and today I will walk you through some of the work we did in University of California, and then some of the plans we have for Chicago and Argonne National Laboratory. Actually, Jennifer's introduction was so good, I can skip some slides in my talk, but I do want to emphasize, first apologize on behalf of the battery field people. We suck at the unit because no one knows what's amp hour, really amp hour. Actually, just to translate, you times the capacity times the voltage, 4 volt, you get the watt hour number. Okay? And the watt hour is a very large unit, 3,600 joule. So in your cell phone, 10 watt hour, typically, you have about 36 kilojoule of energy. So it's quite a lot of energy in your small cell phone. And the battery history actually coincides very well with the industrialization 1.0. I know that we are at the 4.0, but battery is really the key enabler for a lot of the interesting things happening in history. I think Sir Alexander Volta's invention for the Volta piles, you still use it today in the AA, AAA batteries. That a 200 years over technology are actually a commodity in your daily life. And the French scientist Planté also had contributed to lead acid batteries. That's been over 160 years. It's the first battery technology over terawatt hour scale. Olshansky's nickel metal hydride batteries, actually Toyota Prius, I drove that for 15 years before switching to Tesla. Again, never been replaced. We still use that battery technology. And the youngsters among the battery technology, lithium-ion batteries, commercialized in 1990, but not until 2019 that the Nobel Prize for intercalation chemistry was given to 3 gentlemen. 2 of them, we all had the opportunity to interact with, Professor Whittingham and Professor Goodenough, because they are very actively involved in the Department of Energy programs. The whole history taught us something important, is that when we invent new battery chemistry, we enable new battery chemistry, we don't replace the old ones. Okay? A lot of people challenge me about the Moore's law about batteries because we don't double the energy density every 2 years. We do double the capacity every 2 years. Okay? So that's very important to remember that when we invent new battery chemistry, new applications will be unlocked. Things that you used to think it's impossible will be made possible. And when we think about the holy grail for the grid storage, I want to remind people that the batteries installed in the cars and the semi-truck and possibly in electric planes will become part of the grid. It is just a matter of time where vehicle to grid dual direction connections will be entirely possible. And we have to really think about how the entire infrastructure is going to be changed because of the new battery types that is coming on our way. In terms of the nanoscience, I think Kavli Institute really, Nanoscience Institute emphasized on the nanoscience. I just want to say the battery community benefited tremendously from the advancement in the nanoscience. Actually, a battery, the simple cell phone batteries you have has 10 to 20 layers of this so-called single cell. A little bit like the biological systems, a very complex system is made of many cells together. And the first box is what we are currently having in our pocket called intercalation chemistry. And that's what led to the Nobel Prize. And I want to say that it's critical to realize two important messages. First of all, in this closed system, because there's no matter going in and no matter go out, so it is a thermodynamically closed system. If we teach the thermodynamic equations, you actually have to use the mass conservations in your equations. And that's fundamentally different from the fuel cell. In the fuel cell, you have the fuel installed in the tank outside. The device is a conversion device. However, here, you have to do both, the storage and the conversion. And that made the job very challenging for material scientists, because every time we shuffle lithium from one electrode to the other, you are breaking the chemical bond and then reforming the reformation of the bonds. And during this process right now, unfortunately, we have to use a liquid electrolyte, okay? And this liquid electrolyte actually is thermodynamically unstable with both electrodes at either very reductive potential or very oxidative potential. And this is where all the weak links start to, we have the flammability problems, we have the degradation. But even within the intercalation compounds, we took an approach in Argonne National Laboratory using synchrotron to observe batteries while they are operating. So in the highly coherent X-ray, you can actually capture many, many particles, how they transit with the electrochemical signals. And then during the discharge, you can see phase changes, volume changes, and the process is completely reversible in a functional batteries. And this process has to repeat thousands of cycles. So what does that remind us as a material scientist? It's like the airplane taking off and the landing. When we learn the metallurgy, anytime when you have this kind of stress strain phenomena, fatigue is a very important challenge. So the battery community spend a lot of time solving this challenge in the reversible phase changes and the volume changes in small percentage of volume change. Okay, because we're in intercalation. Now, the desire of moving towards a higher energy density, so people demanded 500 to 600 miles per charge for electric cars. And we take the challenge very seriously, because there's no reason electric cars do as good as internal combustion car engines. We have to do better. So when we move towards non-intercalation chemistry, materials like silicon or even pure metallic metal, like lithium metal. On the cathode side, because of the supply chain issue with nickel and cobalt, we are moving towards complete metal-free. You use sulfur as the energy carrier for the host for the lithium. And all of these have to be done with the restriction we are in the thermodynamically closed system. So efficiency has to be, the Coulombic efficiency has to be extremely high, because every side reaction causes you loss of energy carrier, which is either lithium or sodium ions. So this becomes so challenging, and the weakest link in the cell is always at the interface between the electrode and the electrolyte. And this is where the nanoscience, the progress, the tools we build in nanoscience made major contributions in understanding either the anode solid electrolyte interface, which is in the extreme reductive environment, or in the cathode side that we call the cathode electrolyte interface, is in the very oxidative environment. So you could think of batteries as a playground for material scientists who are focusing on interfacial science in the extreme conditions, very reductive or extremely oxidative. So you can already find the similarity between the battery and the fuel cell people, right? So the roadmap Argonne National Laboratory has, when our first storage hub, JCESA, was established, this is a figure almost 8 years old, lay out really well around 8 years ago where the electric cars is, where the roadmap for scientists is. And if you notice, the x-axis is energy density per weight. The y-axis is energy density per volume. And the reason these are plotted, very important to realize the difference, is that if I put another 10 grams in your cell phone, you probably will not complain, right? But if I put another 10% volume increase for your cell phone, I think a lot of people will complain. So different applications has the different restrictions. So when we think about electric vehicles, typically volumetric energy density matters a lot. Okay? Now, when we think about flying drones, flying cars, we think the gravimetric energy density is more critical. And this map lay out clearly two very important research directions. Is that one is that lithium metal as a holy grail must be enabled. And 50 years ago, in the 1970s, the first generation lithium metal batteries, rechargeable lithium metal batteries, completely failed. Okay, completely. All the startups companies failed. And we have to do this again 50 years later. The second important message is that on the new chemistry, we will be forced to enter so-called non-intercalation chemistry. And this is a territory a lot of material scientists are quite dreaded, because we know to deal with 20 to 40% volume change instead of 2 to 4% volume change is very challenging for us. So good news is Jennifer's talk showed the reduction in the size of the cell phone. I just have to tell you, last 10 years, the cell phone size stayed the same. But now you use the cell phone to do TikTok, video watching, GPS, and everything. So you don't realize the energy density has been tripled since the commercialization. And we will show you the pathway for extended the cycle life to 6,000 to 10,000 cycles. And this is where the true enabler for the vehicle-to-grid dual direction exchange of energy will happen. And the recycling of lithium batteries is happening now. We are not doing a great job. After 30 years of commercialization, right now only 20% of the world of the lithium batteries is actually recycled, and we're still debating who should pay for the recycling. And this is one of the major policy issues that's still not resolved. And we have another big challenge before I dive deeper into the science. It's okay, you can't recognize the company name. Just look at the color. Red is China, blue is South Korea, yellow is Japan. The rest of the world is that 10% over here. This is today's picture for lithium-ion batteries. So the question a lot of people ask me is, what do we do now? And I want to remind people to put everything into perspective. Okay? So today, lithium-ion batteries is, after lead acid, the second battery technology that reached terawatt-hour scale. This year, for the first time, our world production will be over terawatt-hour. What does that mean? 1 terawatt-hour battery will power the entire US grid for about 1 hour. Okay? So that's the scale. And the vision for us for the future is that if we want to truly enable renewable energy, around 200 to 300 terawatt-hour batteries will be needed. And I list out a few bullet points where the large amount of batteries will be needed. And that is under the assumption that hydrogen, thermal storage, hydro will all have to come into play, because the battery itself will not solve all the storage challenges that we are facing. And under these circumstances, the prediction by different agencies and the companies is that the whole world will need around 200 to 300 terawatt-hour batteries. So we are about 1 or 2% down with our job. So when you put things into perspective, I think we should realize there's still a lot of work left to be done for storage, right? So the next decade for energy storage, I already mentioned that we will have to build batteries ultimately very safe, even deliver very high energy density, batteries that become an asset, not as disposable. You will never want to put the batteries into the landfill in the future, and can be 100% recycled, because when we take elements from the mining, we already have to be mindful about how the elements are refined, put in the batteries, and recycled. And for United States, I think I try to get rid of this demand, but it's not possible. We are in US, no one is patient, 5 minutes. Yeah, I'm from Singapore. In Singapore, nobody say, I want fast charging in 5 minutes. They are very happy with, because the whole country is 90 minutes, you are driving out of the country, so nobody needs the fast charging. But anyway, the direction for next generation, I know there's a lot of students in the audience as well. The direction, there are multiple routes to achieve those goals. Today, I will first start with sodium and then talk a little bit about the reactive metal, lithium, what can it do? And then I think the solid state is the part that really, personally, I'm extremely excited because I was trained in semiconductor industry, and I really see in the transistor, in the solid state lighting, how solid state science really transformed the science. And I think the battery field will experience the same in the next decade. Okay, so first the sodium. I think the sodium ash deposits has been really surveyed well in the US. US have sufficient sodium ashes to support a lot of the building of the sodium batteries for grid storage. And if we do very simple analysis of the need on the electric grid versus the need on the vehicle, we are talking about the 3 magnitude differences in the demand of the raw materials. And that's the reason why building sodium-based batteries is a no-brainer. And the sodium batteries actually can use most of the gigafactories infrastructure that's already been built for lithium. And I think the research we're doing has to be rely on the physical property of. So let's take a look at the sodium. In the 1960s, the French scientists actually started the sodium battery research way before lithium. If you look at the electrochemical standard potential, most of the sodium analog of the lithium compounds has slightly lower voltage, about 300 milli-electron volt differences, right, in the voltage. So the downside is, of course, the relative mass for sodium is big. So a lot of people in the early days just think, oh, volumetric energy density, sodium have no way to compete with lithium because per volume you can only store less sodium because the size. Now, when we talk about the grid storage, of course, the priority change. And then the other important thing is really the distribution. And I think sodium batteries in the recent 10 years return to the research scene. And I also want to point out the low melting temperature caused a significant concern about the sodium safety. But I want to say when we do reactive metal dendrite formation, sodium is more difficult to form dendrite because at room temperature it always tends to smooth out because the low melting temperature. So sodium actually come back to our research field starting about 2012, and in the last 10 years I want to show you some interesting development work that happened in my research group, the power of sodium battery. So if I use a sodium it's like an intercalation material, sodium metal anode. If I use the traditional electrolyte we developed for the lithium, okay? The cell, okay, this is not good, right? You charge, and then when you discharge, you get like 50% or 20% of the capacity. And again, I apologize for the jargon. When we say 5C, it means C 60 minutes over 5. So it's 12 minutes charge-discharge. So this is a pretty fast charge-discharge protocol we do for sodium. The key here is that when we research on a new chemistry, you cannot assume everything we learned in the lithium can be directly translated to sodium. That will be a mistake. Okay? So through a lot of the new electrolyte search, the new sodium batteries can demonstrate, so sorry about all the redness, but if 20C, you can see the 3 minutes charge-discharge, the cell can actually deliver 80% of its energy density. So this is one of those exciting developments to show when people work on new chemistry, the materials, the chemistries, you have to redesign everything. And in principle, this is sodium batteries can really deliver very, very high capacity and the power. And I started working on sodium from my NSF career world a long time ago. It really took a long time to develop the right cathode, right anode, and the right electrolyte combination. And Bharat graduated to show this is a definitely viable approach. And then 2 other very brilliant students decided to take the technology to give a try. And I want to emphasize I just came back from Germany last night. The German students all tell me they absolutely do not want to do startup because there's no ecosystem there. In the United States, I think we are very fortunate that we have students, those who declined offer from Tesla and highly respected companies to do startup themselves. So I hope a few years later, you will have sodium batteries on your hand. I would want to promise less than 2 years, you should be able to. And we're still behind China because they already put the sodium batteries in the low driving range electric cars, because in China, they really want to reduce the cost, so those batteries are already being put into the cars to test. The topic of my favorite is the so-called solid-state batteries. So I hope in the future, when you come to my lab, I could let you experience the magic where you cut batteries and the device will still be on. And those are important to realize that the solid-state batteries, because of the electrolyte is so safe, you can potentially enable extremely high tolerance of abuse. Of course, we really don't want people to do this to the batteries. Please don't. But there's another important opportunity come with solid state. As I mentioned in the solid state lighting and the transistors, the interface control between the different solid state materials were so precisely done that they can transport electrons, phonons so well. Now it's time when people in solid state science really think about how you transport ions through solid you And that comes with also a possibility for us to reinvent the entire manufacturing process. I know that there's a lot of doubt about whether US will catch up the Asian catch up for the manufacturing. I will tell the whole audience with confidence, if we try to reproduce what they do, the game is over because they already had 20 years of lead time. But if we try to do solid state, where we have really good know-hows and hardwares to do solid science, I think there's a really great opportunities here. The solid state will also enable so-called bipolar design. Today, I don't have time to go through this, but there will be certain architecture for batteries. You can have one battery with 8 volt. It's possible if you can get the bipolar design. And those new concepts should be what we focus and try to pursue in the future. So solid-state battery is a platform technology, which means it's chemistry agnostic. You don't mind which chemistry the person or the company choose. You can choose a cathode that based on different chemistry. You can choose anode with lithium or silicon. I want to show you about a few years ago when we started the solid state, the energy density climbed very slowly until we have some companies, actually researchers plus companies, realized a very thin, robust 30 micrometer pinhole-free solid-state electrolyte. The energy density jumped up to be comparable to the lithium-ion batteries. And then moving forward today, I want to show you some fascinating data on how we can actually enable lithium metal or pure silicon as the solid state. And this is something in the liquid, very difficult to do, but we can do it in solid, and I hope I deliver the message clearly. And then, of course, everything we do on the lithium, sodium can have its analog, even though volumetrically I draw a bigger box. I think we should all realize sodium is not directly competing with lithium in the mobility applications. Okay, so solid state, the chemistry that can be used for cathode is very rich, okay? From lithium cobalt oxide, single crystal, you can see that large crystals, but cobalt, again, very unsustainable because right now in all the product in the car, the cobalt is less than 5% of the total cathode materials. The manganese-rich materials is the direction to go, and you probably have heard that lithium iron phosphate, in fact, I don't know, see Dr. Brandon Foots, Professor Foots' group is one of the first few research groups in the world to produce the proper lithium iron phase diagrams, lithium iron phosphate phase diagrams in the batteries. These materials of 30 years old is actually coming back to really kind of de-risk the supply chain, because iron phosphate is really, should be very, very low cost. On the electrode side, we have a challenge here is what cathode pair with what electrolyte. So there are many types of oxides and sulfides, chlorides, borides. So the solid state chemistry, the space is vast. And we have to actually think about what is the suitable pairing between the active cathode materials and the electrolyte, and etc. So I don't have time to dive deeper in the details, but just to give you a sense about how rich the solid state chemistry is. And then you can already guess I will go to, you probably will need some help from computation, AI, and then those things. But from the pure materials processing perspective, these two persons actually, particularly Dr. Ji-Hyun Jang, actually quit his job in Samsung and come to do postdoc with me. And he actually, with the magic hands, showed me that you can make in an academic research laboratory all solid-state batteries assembly. It's absolutely possible because the innovation in the solid-state processing. And of course, we are a research group. We are not trying to make the best batteries, but we're trying to challenge what can you do in solid state science that liquid cannot do. So I'll just say one story about where we truly demonstrate solid state is unique. Okay, so there is an anode materials called silicon. In fact, silicon it's a favorable topic for many battery researchers since 2006, because each silicon can take up to 4 lithium. So its energy density is at least 10 times higher than that of the graphite, the one that currently used in our cell phone. Now, people make a very sophisticated nanostructure of silicon to combine with the carbon and the binders, and then they put in the liquid. Now, the challenge is when silicon and the lithium alloy, the volume expansion is typically 200 to 300%. Because silicon take up so much lithium, so you could imagine that when these silicons start to expand, what's going to happen to the electrolyte that has been penetrating in the pores? Because in liquid, you have gravity. You cannot prevent the liquid to penetrate through all the pores inside a silicon electrode. And because of that, we had a lot of tremendous amount of degradations happen in silicon. So since 2006 until today, 18 years have passed. Silicon loading in a smartwatch is about 5 weight%. So they add very little to improve the energy density a little bit, but because of this challenge, silicon actually could not make into the electric cars because nobody wants to just risk to have 5% energy increase, but then risking the cycle life degradation, because each of those volume expansion shrinking will cause the degradation and the cycle life degradation. So for almost 2 decades, silicon, even though very promising anode materials, could not make into significant impact into the batteries. So let's think about what happened in the solid. In the solid state electrolyte, what we can do is that because the particle size can be precisely controlled, okay? So imagine if your particle size for the solid electrolyte is relatively larger compared to the pores inside the silicon. And you just build a porous silicon anode, but without any of the carbon additives in it, okay? So first glance is that this is an interesting thought experiment. The reason we do that is we think because even gravity is there, the solid cannot flow. There is no flowability for the solid to go to the pores. So the hypothesis is that when you do electrochemical process, all the lithium will be driven from the cathode to the anode under the electrical current, and this lithium silicon alloy should proceed without any interference of the electrolyte interference. So it is a complete solid-state alloying process driven by the electrochemistry process. So what happened to lithium silicon, if the volume will expand, but it will expand in the pores completely, plus some volume expansion. Of course, there will be some volume expansion. And this process will produce 100% dense lithium silicon alloy that you cannot do it in the liquid cells. So that's the thought experiment. And one important thought requirement for this silicon to work is that you want to use cheap metallurgical grade silicon. We don't want the fancy ones where the surface are usually covered by a lot of oxygen, so the electrical conductivity will be impacted, because the concept will only work if you have a true mixed conductor where the electron and the ion will be conducting through this process. So in the cell, when you make the silicon, this is a completely random. Even you see the particle size have varies a lot. It's something we buy from Sigma Eldridge with extremely low cost. And when you do the process, lithiate this, in fact, almost completely pore filling. And when we shine the X-ray on this silicon, it's a beautiful silicon crystals. When we do it at the end of the charge, completely amorphous. There's not a single signal of crystalline signal. So this is also one of the reasons to understand what we made. It's very difficult. So a lot of people are using more of the pair distribution function, total scattering method to understand the structure of lithium silicon. Now, the most, this is a reminder to myself, I should wrap up. So when you actually take lithium back, the pore formation is vertical, and until today, the paper has been out for 2 years, and we still couldn't fully understand what happened in the pore formation up the discharge process. Okay? Yeah, so I just want to show you the initial volume expansion is real. You have almost 100% volume expansion, but when you discharge, you form a stable structure with 30% of pores, and the stable structure actually do not change upon further cycling. And this is something we created in the solid state cells, which you will not see in the liquid cells. So there's a lot of coupled chemomechanical properties of lithium silicon that we do not fully understand yet. So the battery property is a bit boring because it just shows you it can cycle a long time. But I think solid state finally reach a stage where we can talk about how we can enable 500 miles per charge, because the energy density will improve significantly. And the last part of my talk, I just want to quickly say several things about the lithium metal. I already mentioned that lithium metal was considered as holy grail, but for 50 years, actually the first generation lithium metal battery is 1976, the science paper. The lithium cobalt oxide, iron phosphate, nothing has been invented, so we have no cathode, no lithium in the cathode. So this is the first generation. Now we can do this in the proper high energy cells, but lithium metal actually, we made a lot of progress in the last few years. When we first started, every cell failed after 50 cycles. And I'll show you why the lithium metal is so difficult to observe, because actually the tools we have is not good, because the gallium Fib beam will interact with lithium. So we have to bring it to the cryo temperature. But just this simple tool advancement explain why the early lithium metal cells cannot work. You look at this is the electrochemically deposited lithium. More than 50% of that is pores. okay? And then when we change it to the new electrolyte developed by the National Laboratory, Pacific Northwestern, you can finally get the lithium that is 100% dense. And I think Jennifer and I have the common interest for cryo-EM, where you can like decipher where is the loss and how. This is a typical image of lithium metal, completely surrounded by the SEI, and it could not perform its job as a lithium metal anode because the electric pathways were cut out. Okay. All right, so I think we are almost at the end. So I just want to maybe say a few things before I wrap up. Okay, so there's a problem for the battery field. I think up to this year, from 2000 to now, cumulated battery paper is skyrocketing. Okay, over 30,000 papers. And Dr. Kangshu told me about 150 papers published every week. So I think I have to assign an undergrad student full-time just to read the papers and summarize papers. Okay, so here I think for all the folks who are working in these kind of super emerging and the popular topics, we really have to think about what to do. Okay, so this is, I would say, where the future direction for battery research is have to figure out how we handle this, because in principle, we cannot even compare the results from different groups because everyone is using different methods to study their battery materials. So that's problem number one. Problem number two is the scaling, science for scaling. It is much less emphasized in today's curriculum for students. So I want to say we should stop debating about a battery is good for mobility or not. It is absolutely good for e-mobility, okay? Battery 300 watt-hour per kilogram is already reached. We already reached that energy density at a pack level. That's about 1 megajoule per kilogram. And that's the entire battery pack. Well, when people talk about the liquid fuel, 40 megajoule, hey, you have to divide by the weight of the engine. So we should not debate whether batteries is good for electrification or not, right? We should move on to think about the future directions. And I think that it's really critical for us to think about what is the thermodynamic limit for how long battery can last. I could not find any. So if someone could enlighten me, we think you can continue to improve the cycle life, reduce the degradation of batteries for many years to come. So batteries can go to 10,000 cycles or even longer. And the last part, I think very much underinvested in all the engineering school is we don't really think about the mining, manufacturing, and how do you reach the sustainability goal for batteries. Remember, battery is not renewable. We are not renewable. We take elements from the ground, from the Salt Lake Bank. We make them into batteries, and how we make the batteries, how you use the battery, how you recycle the batteries will ultimately decide its carbon footprint. And for now, I think Asians are leading in the manufacturing, but they are completely ignoring the sustainability factors for now, okay? The numbers look very bad, actually. It takes more than 35 kilowatt hour electricity to make 1 kilowatt hour batteries right now. Yeah. Okay, so yeah, I think if you are in, anybody here is in investment, yeah, we are asking for a $1 trillion investment. Yeah, so okay, the collaborator, the fundings, my alumni and the current group, and I am like a delocalized electrons to travel between Chicago and San Diego, still quite a bit. So yeah, that's only possible because so much of the support from the federal agencies and industry partners. So thank you very much. I'm happy to answer questions.
Please repeat any questions.
Yeah, I think we have time for some questions. Julia.
Hi, I'm here. So Shirley, thank you. This is a fantastic overview of what's happening in the battery sector, and actually quite a few of us here are very interested in this. So thank you for that. The question I have is, you mentioned that there are bonds that are forming and reforming, of course, in any rechargeable battery, right, in the cathode and the anode. What about in the electrolyte? How the ion coordinates with what's happening, polymer gel electrolyte versus a solid state electrolyte versus liquid.
Yeah.
Comment on the bond formation and dissociation in the electrolyte?
Yep, I think that's a really good question.
Actually, can you repeat the question?
Oh yeah, sorry about that. The question was, so for folks on the Zoom, the question was that can I explain the bond formation and the breaking processes in the electrolyte, because we only talk about the electrodes just now. I think this is an absolutely important question. I guess, we'll also review part of the plan. What we're going to do in Argonne National Laboratory is really try to decipher all the bonding processes in the electrolyte. Okay, so the reason I showed you in the sodium batteries that electrolyte enabled a 1.5 minute charge and discharge is because in the traditional electrolyte, we have so-called the solvation structure here, right? So solvation structure in the liquid is each cations will be surrounded by multiple anions. So when you are moving, you're dragging, you're not just moving yourself, you're dragging all the anions around you. So that's why in the liquid electrolyte, the transference number is very low, even though the conductivity number is high. But if you think about, the process, when you drag all the anion to the electrode, you still have to desolvate all the anions and to enter the solid. So this process, I would say, is the driving force all of us are working on single ion conductor for polymers, solid state, because in the solid, this process is mostly believed not to be the right conduction mechanism. You are actually using, in solid state that they have proposed many other conduction mechanisms, paddle wheel or, polymer chain vibrations, and there are many other mechanisms that prepare the ions to move. So we hope that in the next few years, more researchers will find the so-called super ionic conductors, meaning that in the solid, when the ion moves, it can move at room temperature, the speed higher than the liquid. And I think there have been examples shown by some scientists, and we wanted to kind of replicate this effect in many polymer and the solid state. Yeah, so, yeah.
Maybe time for one
Cynthia.
more question? Oh, yeah.
So very nice talk, Shirley. I wonder if you could, I have a broad question. Could you articulate the biggest gaps in development of solid state batteries, and then what tools you're lacking, both, like experimental on one hand, maybe X-ray spectroscopies, but also theory or the use of AI? Is there a way we can tackle these things quickly?
Yep, very good question, Cynthia. So the question was, can I identify the gap in developing the solid state batteries? Are there, new methods and new spectroscopy imaging methods needed for solid state and perhaps AI machine learning? So I will use this slide to kind of answer this question. So I think that in solid state, the components, particularly green boundaries and empty space like void, play a significant role. So in the characterization areas, what we are really needed is so-called buried interface, analysis of the buried interface. And in the past, the battery field developed the entire suite of tools with the assumption that the liquid can be evaporated. So you can look at the interface when the liquid is gone. However, in the solid, this is mostly unlikely to happen. So I think that's the gap number one. We don't have many good metrology development for understanding the solid interface in electrochemical device. We have a very good tools, like I work with Thermo Fisher for semiconductor industry, but those interfaces, they are not exchanging bondings. They're not exchanging ions. So that's number one. Number two is, I think, connected to Julia's question as well, because transference number is unity in solid-state electrolyte, then the ions can, in principle, go through the solid interface with no barrier at all. However, I would say in reality, no one has actually imaged or measured the actual ion conductions through the solid-solid interfaces. So that actually made our direction for processing optimizations really difficult. Right now, it's more like old ceramic technologies where we just sinter and then hope that we are lucky that we get the good interfaces. So the design aspect is very much missing. That's number 2. Number 3 is the discovery of the new solid electrolytes. So you must have all seen the Nature and the Google DeepMind and the Microsoft. The last month there were a lot of high-end publication came out, and then also Professor Gareth Sater, my former Ph.D. advisor in Berkeley, also released the work about the discovery of large amount of new solid electrolytes. So I think one thing is my personal opinion. I'm not speaking on behalf of Argonne or I think there's a difference between compounds and the materials. So when we say materials, we mean the functionality of this has been figured out. So a lot of times when people measure the conductivity, they are not measuring them in the actual devices. They are doing certain physical properties measurements, and the new compound that reported by Microsoft or Google DeepMind, in my opinion, cannot be called materials, because the materials have to be investigated in the actual functioning environments. So that's where the third gap, in my opinion, is that all the experimental work for evaluating materials properties are not high throughput yet, particularly characterizations and performance measurement. So that is the third gap I believe a lot of us have to invest time and instrument to work on that. Yeah.
All right, if there are no further questions, let's thank Shirley for an incredible presentation.